maybe things will work. Okay. Welcome back from spring break. Let's see how mine's going so far this morning. You have a test a week from today, do you not? So we're going to do chapter 7 today. It's actually fairly short. It's on the central limit theorem. And then on Thursday, we'll do a little bit of chapter 8, not a lot, just a little bit. So you can get ready for your exam, which is due on Monday, the 27th at midnight. Okay. So we are going to cover the central limit theorem today. And as I was, not that my family is odd or anything, but my family is odd and everything. I remember what evening it was. I had my granddaughter over spring break, and her mom and dad came to get her, and we all went out to dinner before she went home. And at dinner, she's 4 years old. She'll soon be 5. She was having me do math with her. So if I have 4 and I have 3 more, how many do I have? So we were doing, if you have 4 and you have 3 more, how many do you have? And she was writing the number down. So last night at dinner, my husband and I were discussing the central limit theorem and why it is so important in statistics, because it's extremely important. So we're going to talk about the central limit theorem. We're going to watch a video first thing this morning. And then we're going to talk about continuous distributions and why a particular problem you use the normal distribution or you use the central limit theorem. There are key words in your homework problems that you're going to want to look for. And then we'll talk about the central limit theorem for means. So why are we so concerned about means, averages? Because they give us a middle ground for comparison and they're very easy to calculate. And in this chapter, we're going to look at the distribution of sample means. So given a population, taking a sample, calculating the mean, looking at the distribution of those sample means. Okay, we're going to watch the video. Everything okay? Guess we'll find out when she starts talking.
Hi, I'm Betty, and this is Against All Odds, where we make statistics count. In the 3rd grade class, out of Ross School in Ohio, California, 20 rambunctious 9-year-olds were about to become a living demonstration of how, with the right statistical tools, we can use samples from a population to make inferences about the population as a whole. Remember, we get statistics from sample data, while parameters are generally unknown, because they describe an entire population. Here's our population. The 9-year-olds at Monica Lass, lining up according to their height. 50 inches at one end, 57 inches at the other, with most of them clustered around the center, near 53 or 54 inches. This is our population distribution, the distribution of values in our whole population of 9-year-olds in the class. When we plot this out, you won't be surprised by now to see that the shape of the distribution is approximately a normal curve, from which we can calculate the exact mean.
All right, so just measuring the heights of these kids and looking at the distribution of these 20 kids' heights, we would expect them to be normally distributed because that's one of the measures that is normally distributed, and they are.
New 53.4 inches, and the standard deviation sigma 1.8 inches. Okay, now we're going to take some random samples from our population. Here comes the first sample of 4 students. Throughout this example, we're going to stick with 4 as our sample size. Once again, we calculate the mean. In this case, the sample mean, or X bar, which comes out at 53 inches. Now we take a different random sample. This time, the sample mean is 52.25 inches. From a third random sample, we get an X bar of 52.75 inches. From a fourth, a different distribution, but an X bar that happens to be the same as the last. And from a fifth random sample, we get a sample mean of 53.25 inches. We can keep going until we've selected all possible samples of 4 from our population of 20. And now we can plot out all the sample means we calculated. What we get is a distribution of our sample means. Or to put it another way, sampling distribution of X bar. A distribution of X bar values from all possible samples of size 4. And like any distribution, it can be described by its shape.
Okay, so what they did is they took every possible sample of 4 from these 20 kids, all the different possible samples, and they took the mean of each sample. So they get the 4 kids, that's the sample, they measure their heights, they take the mean of their heights, and that's what they plotted here. So this is a distribution of sample means.
And spread. The shape is our familiar normal curve. The center is the mean of X bar, 53.4 inches, which is exactly what we got from the mean when we calculated it from the population as a whole. But when we directly compare the population distribution to our sampling distribution, we can see that while the center is the same, the spread of the sampling distribution is much less. In fact, sample means are always less variable than individuals. That makes sense. A random sample should include a variety of individuals. From our population, some short, some medium, some tall. The sample mean literally averages out that variety, so we see less variation. There is a precise relationship between the standard deviation of the sample mean and the standard deviation of the individual heights. Here it is. The standard deviation of the sample mean is simply the population standard deviation divided by the square root of the sample size, in our case 4. So the standard deviation of our sample mean is 0.9 inches. Let's see how we can put this fact to use in a situation with board stake for figuring out the average height of a 3rd grade class. A manufacturing plant with circuit boards. Actually, this is a scene you don't see that much anymore. An electronics manufacturing plant in the United States. Today, many electronic assembly plants are overseas and involve components that are a lot smaller than these. But we are interested in how statistics helps control quality of manufacturing, and those principles haven't changed. A key part of the manufacturing process is when the components of the board are connected together by passing it through a bath of molten solder. If things go wrong, say the temperature of the solder or the speed of the conveyor isn't right, then the connections on the boards will be faulty. Workers can't wait until the boards reach the end of the line to spot a problem that's occurring here. So after they pass the soldering bath, an inspector randomly selects boards for a quality check. The score of 100 is the standard, with some a little higher, some a little lower. The natural variation inherent in any manufacturing process. The goal of the quality control process is to spot if the expansion starts drifting out of the acceptable range, suggesting a problem with the soldering bath. Here's the distribution of the quality score. The normal curve centered on 100. Its standard deviation, derived from the company's experience with the process, is 4. So how does what we've learned about sampling distributions help quickly spot when things go awry? The inspector's random sampling of the boards has a sample size of 5. Let's see what happens when we take repeated samples. From our first 5 boards, we get an X bar of 99.4. From our second sample of 5 different boards, we get a different X bar, 101.6. We keep on sampling, calculating each X bar, until we can start building a sampling distribution, which is, as expected, centered on the mean of the population, 100. But it has a smaller standard deviation of around 1.79, as you can see from the formula. Here's how this is useful in the statistical quality process known as the X bar control chart. The inspector plots the values of X bar against time. As expected, there's variation. The goal of the process is to distinguish chance variation from the extra variation that shows something is going wrong. Here's the normal distribution of X bar. If everything is going well, the mean will be at 100. Now recall the 68, 95, 99.7 rule for any normal distribution. Almost all observations, 99.7% in fact, will lie within 3 standard deviations of the mean. Going out 3 standard deviations from the mean gives us what this quality control method calls control limits. As long as the quality scores remain normally distributed with mean 100 and standard deviation 4, that is, as long as the soldering process continues its past pattern, almost all the X bar points in the chart will fall between the control limits. The process is said to be in control when its pattern of variation is stable over time. The point outside the limit is evidence that the process has become more variable, or that its mean is shifted. In other words, that it's gone out of control. As soon as an inspector sees a point like this, it's a signal to ask, what's gone wrong? So far, we've been talking about population distributions that follow a roughly normal curve. What if we were to take a very different population distribution? The mayor's 24-hour constituent service hotline in Boston answers hundreds of thousands of calls every year. The operators handle everything from simple requests to more complicated questions about city services.
Typically, people call to report things like potholes or streetlights that might be out in the neighborhood.
People that trash out too early, or people that trash out too late, or people aren't keeping their property clean. From some street that is a major four-lane street where they say there's a truck running down the middle of the street. There's one where a skunk got stuck in a revolving door. I had one recently about a little boy who wanted to class speak for a mark painter with a horse. The thing about calls to this, most other call centers, is that the length of the calls varies widely.
So the average length of our calls. Say that in range.
Most calls are relatively brief, but a few can just go on and on. The mayor's hotline answered a total of 21,669 calls in 1 month. If we plot the length of each call, the variable, against the number of calls, we get a distribution sharply skewed to the right. You can see it on this density curve, representing the month's call durations. If we sampled from this population, would our sampling distribution also be skewed to the right? You might expect so, so let's find out, using different sample sizes, starting with samples of size 10. Let's take our first sample of size 10. For this sample, the mean length of the calls is 98.7 seconds. We can start to build a histogram using the sample mean. Let's continue taking samples of size 10, each time finding the mean of the sample and adding it to our histogram. This final histogram is based on 40 different samples of size 10. We can do the same thing with 40 different samples of size 20. And finally, we can do it again with 40 different samples with an N of 60. Now let's compare our sampling distributions with the original population distribution for all calls to the mayor's hotline. The spread of all of the sampling distributions is smaller than the spread of the population distributions. And you can see that the spread of the sampling distributions tightens still further as the N increases. Interestingly, while the smallest sample size with an N of 10 is still right skewed, the asymmetry decreases as the sample size gets bigger. By the time N equals 60, we've lost the skew and the sampling distribution of the sample mean looks pretty much normal. The normal quantile plot of X bar data of 40 samples of size 60 looks like a pretty straight line, underscoring that our data are normal. This happens because with larger samples, we are less likely to get all big or all small numbers. We usually get a mix. Some X bars will be above mu, some below. So we get an approximately normal shape for the sampling distribution, even though the parent population isn't normal. What we've uncovered here is one of the most powerful tools statisticians possess, called the central limit theorem. This states that regardless of the shape of the population distribution, the sample distribution of the sample mean will be approximately normal if the sample size is large enough. It's because of the central limit theorem that statisticians can generalize from sample data to the larger population. We'll be seeing how that can be useful in later modules about confidence intervals and significance tests. Stay tuned. I'm Party Sabetti for Against All Odds.
All right, so what this says is I have an underlying population distribution that is decidedly not normal. The call center taking calls, the distribution is skewed drastically to the right. Because the call length, you get, most of the calls are very short, but then you get a spattering of calls that go on, as she said, go on and on and on. So the underlying distribution is not normal. It's not a normal distribution. But if we pull samples from the data of the call lengths, the larger the sample is, I take the mean of that sample and then look at the distribution of the sample means, that will be normal. And so you can, every distribution can be a normal distribution by looking at the distribution of the sample means. And the larger the sample you take, the more normal your distribution will be. So we'll look at just a second rolling a die. Decidedly not a normal distribution. But if we roll more and more die and then take the average of the numbers on the face of these die, and we look at the distribution of those averages, it will be normal. That's incredibly important. So the central limit theorem is one of the most powerful and useful ideas in all of statistics. There are two alternate forms of the theorem. Both alternatives are concerned with drawing finite samples size n from a population with a known mean and a known standard deviation. The first alternative says that if we collect samples of size n with a large enough n, so a large enough sample size, which we'll discuss more in a minute, calculate each sample's mean and create a histogram of those means, then the resulting histogram will tend to have an approximate normal bell shape. The alternative, which we don't really look at in this course, is if we collect samples of size n that are large enough, calculate the sum of each of those samples and create a histogram, it will also be approximately normal. So we can look at the central limit theorem in both terms of the averages of our samples, the means, or the sum of our sample. And we really don't look at the sum in this course. So the distribution of sample means is normally distributed if your sample size is large. The size of your sample n that is required in order to be large enough depends on the original population from which the samples are drawn. The sample size should be at least 30, or the data should come from a normal distribution. So for our children, when we were measuring their heights and looking at the distribution of the average of the sample, it didn't matter that we were taking samples of size 4, because the underlying distribution of the heights of these children is normal. So if the underlying population has a normal distribution, it does not matter what sample size you take. If the underlying distribution is not a normal distribution, then a sample size that is large enough is typically 30 or more. If the original population is far from normal, the more observations are needed for the sample means or sums to be normal. So as she was saying in the video, the larger our sample size, the more variation we get in the values, and the averages become more normal because we kind of eliminate the variation we get in the actual data values. By taking the averages, we eliminate a lot of the variation in the individual data values. Sampling is done with replacement. So when we looked at the 20 students in the 3rd grade of that school, we did do the samples with replacement. We took every combination of 4 kids that we could possibly take out of the 20. It would be difficult to overstate the importance of the central limit theorem in statistical theory. Knowing that data, even if its distribution is not normal, behaves in a predictable way is a powerful tool. This is one of those in college algebra, I say, I feel like, the heavens should open and the angels should sing. I said, they need to get sound effects. This morning in college algebra, we were doing synthetic division. And I say, do you know how important this is? Do you know how important this is? It should be, that's how important this is. Same thing. If you want to figure out the distribution of change and that people carry in their pockets, do people carry change in their pockets anymore? I don't think so. Using the central limit theorem, assuming your sample is large enough, you will find that the distribution is normal and bell-shaped. Okay. Central limit theorem as it pertains to averages. The central limit theorem for sample means says that if you repeatedly draw samples of a given size, such as repeatedly rolling 10 die. So if you roll 10 die, that's your sample size, and you find the average of the faces of your die and calculate their means, those means tend to follow a normal distribution. So if I roll a die, the distribution of rolling a die is uniform because each phase has exactly the same probability of occurring. And we'll look at this in just a second. But if I look at the probability of getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6, each one of those has a 1/6 probability of occurring. So rolling a die is decidedly not normal. It is a uniform distribution. But if I roll 10 die, find the average of the faces, and then plot the averages, then what I'm going to find is that distribution tends to be normal. Now, again, since this is a uniform distribution, decidedly not normal underlying distribution, I should probably roll 30 die and find the averages of all 30, because that would give us a more normal distribution of the sample means. As the sample size increase, the distribution of means more closely follows the normal distribution. So if I roll 10, I get something somewhat normal. But if I roll 30 or 40 or 50 or 100, the distribution of the sample means will become normal. The normal distribution has the same mean as the original distribution. So the central limit theorem doesn't affect the mean. The mean of the sample distribution will also be the mean of the population. But what happens with the standard deviation? So you have a population with a particular standard deviation. If I look at the distribution of the sample means, that variation is going to decrease. The distribution of sample means has a smaller standard deviation than the population. As a matter of fact, it's a predictable smaller value of standard deviation. The standard deviation is the square root of the variance. So the standard deviation of the sampling distribution is the standard deviation of the original distribution divided by the square root of n. So if I have a distribution that has a population standard deviation of sigma, then the distribution of means So now looking at the distribution of the sample means, we'll have a standard deviation of sigma over the square root of n. So if you're looking at a problem and you're looking at the distribution of sample means, you're going to use a standard deviation of sigma over the square root of n. And that's how you're going to tell the difference in your homework problems. If you're looking at the distribution of your population and you're given a standard deviation, that's the standard deviation you use. But now if you're looking at the distribution of the sample means, the standard deviation gets smaller because the variance decreases if you start looking at means instead of individual data values, and you're going to decrease it by a factor of the square root of n. The variable n is the number of values that are averaged together, so it's the sample size, not the number of times the experiment is done. Okay, so suppose X is a random variable with a distribution that may be known or unknown. I don't really care. It may be any distribution whatsoever using a subscript that matches the random variable. Suppose that mu sub X bar is, mu sub X is the mean of X, sorry about that. So that is the mean of the population. Sigma sub X is the standard deviation of your population. If you draw random samples of size n, then as n increases, the random variable X bar, the distribution of your sample means, tends to be normally distributed. So the distribution of your sample means X bar is normally distributed with a mean that is equivalent to the mean of your population, but the standard deviation of your sample means is the standard deviation of your population divided by the square root of n, which is your sample size. Okay, so here is the rolling a die example. If I roll a die, the probability that I get a 1 or a 2 or a 3 or a 4 or a 5 or a 6 is 1/6. So rolling one die is a uniform distribution. If I roll 2 die and average the faces, so I roll 2, take the 2 dots, whatever the dots are, average them up, and I look at that distribution, it automatically becomes more normal looking. If I roll 4 die and look at the average of the faces of those 4 die, it becomes even more normal. And then if I look at 10, rolling 10 die, finding the average of the faces and plotting the distribution, it's normal. So I can take a distribution that's decidedly not normal, and by looking at sample averages, I have a normal distribution, which is very predictable. I know all sorts of things about the normal distribution. Okay. All right, to find probabilities, you do know how to do that on your calculator. Second distribution, normal CDF. But now if you're looking at sample means, the standard deviation is going to be the standard deviation of the population divided by the square root of n. So that will be the difference in your calculation of the normal distribution. Okay. In a recent study reported October the 29th, 2012, on the Flurry blog, the mean age of tablet users is 34 years. We really need to get some new data, don't we? Suppose the standard deviation is 15 years. Take a sample size n equals 100. What are the mean and standard deviation for the sample mean ages of tablet users? What's the key word here? So if I take sample size 100 from this population and I look at the distribution of the sample means, the mean of this sample means is going to be the same as the mean of the population. So mu sub X bar is going to be the same as the population mean, which is what? 34? But the standard deviation of the distribution of sample means will be the standard deviation of my population divided by the square root of n. So that is going to be what? 15 over the square root of 100. The standard deviation of the sample means is always smaller than the distribution of the data. Always smaller than the distribution of the population. And it's always smaller than the standard deviation of your population by a factor of the square root of n. A recent study reported on the Flurry blog, same study. What does the distribution look like? I don't know what the distribution of the underlying population looks like. But I do know the distribution of the sample means will be normal. So the central limit theorem states that for a large sample size, n equals 100 is sufficiently large. It just needs to be bigger than 30. If I don't know the distribution of the underlying population, I need to take samples of 30 or more. If I know the underlying distribution is normal, then it doesn't matter. So the central limit theorem says that even if I don't know what the underlying distribution of this particular population is, the sample size is sufficiently large enough that if I look at the distribution of sample averages, it will be normal. Same study, find the probability that the sample mean age is more than 30 years. So I have to decide what standard deviation I'm going to use. So what am I looking for? The probability that the sample mean age. So there is my keyword, mean. I'm looking at the probability that the mean age is more than 30 years. So I'm going to be using a mean of 34. More than 30 is over here, isn't it? Yes, it is. More than 30. What's the probability that our mean is more than 30? We're going to be using a sigma of 15 over the square root of 100. And we're doing that because we're looking at the probability that sample mean age is more than 30. So how do we do that? Well, we're going to go to our distributions, our calculator. We're going to use our normal distribution, number 2. Our lower limit's what? 30. Our upper limit's going to be as far to the right as we can go. So we're going to use 1 times 10 to the 99. And our mean is what? 34. And our standard deviation is 15 over the square root of 100. And you can put that in. Your calculator will do the calculation for you. Now I know that's 1.5, but your calculator can do it. So 15 divided by the square root of 100. So your calculator can do that. I do need to close my parentheses. So if you don't want to sit there and calculate the standard deviation and carry it out to 10 decimal places to pluck it in here, let your calculator do the calculation for you. So we're going to do a normal distribution with our lower limit of 30. The upper limit is 1 times 10 to the 99. 34 is our mean. Our standard deviation is 1.5. So the probability that we get age more than 30 is what? Nearly 100%. So what does it say? What it says is the vast majority of users are over 30. Did I even write this down? 0.9962. So 99.6% of our users are over 30 years old. An unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n equals 25 are randomly drawn from the population. Find the probability that the sample mean is between 85 and 92. So our mean is 90. And we want to know the probability that our sample mean is between 85 and 92. And how do I know I'm going to be using the central limit theorem? What's the clue? Well, you're drawing samples. That's a big clue. And what's the other clue? That the probability the sample mean is between these two values. So what's the probability of the sample means between 85 and 92? We're going to use that sigma. That is what? What's our standard deviation? 15 over the square root of 25. So we're going to do a normal. CDF. Our lower limit is 85. Our upper limit is 90. Sorry about that. Our mean is 90 and our standard deviation is 15 over the square root of 25. That is a 92. So go to our distributions. Normal distribution. Lower limit is 85. Upper limit is 92. Mean is 90. Standard deviation is 15 over the square root of 25. And yeah, I know that's 3, but square root of 25 is 5, correct? 15 divided by 5 is 3. Normal distribution 85, 92, 90, 15 over the square root of 25. 0.6997. So the probability that a sample mean is between 85 and 92 is approximately 0.7. I get this question every semester when you start doing this homework for chapter 7. How do I know which sigma to use? And again, it depends on if you're looking at the distribution of sample means or not. And there are problems where they ask you, which one do you use? If you're looking at the underlying population, use the standard deviation sigma. If you're looking at the distribution of sample means, take sigma divided by the square root of n. Unknown distribution with that mean of 90, standard deviation of 15, sample size of n equals 25. Find the value that is 2 standard deviations above the value 90 of the sample mean. Okay, so our standard deviation is the 15 over the square root of 25, which is 15 over 5, which is 3. So 2 standard deviations above the mean, 2 standard deviations would be 2 times 3, which would be 6. add 6 to 90. So a mean of 96 would be 2 standard deviations above the mean. So this is pretty much the same thing you were doing in chapter 6. The only difference is knowing which standard deviation to use. If you're looking at, not to reiterate or drive this into the ground, but if you're looking at the distribution of sample means, you're going to use the smaller standard deviation. It's the population standard deviation reduced by a factor of the square root of n. So you take your standard deviation of your population, divide it by the square root of n. The length of time in hours it takes over 40, an over 40 group of people to play one soccer match is normally distributed. So since the underlying population is normally distributed, I don't really care what sample size we're taking, but we're taking the sample size of 50 anyway. With a mean of 2 hours and a standard deviation of a half an hour, a sample size n equals 50 is drawn randomly from the population. Find the probability that the sample mean is between 1.8 hours and 2.3 hours. So since you're looking for a probability of a sample mean, that means you're going to use the central limit theorem. And you're going to use a standard deviation that is reduced by a factor of the square root of your sample size. So normally distributed, the mean is 2 hours. What's the probability that we get a sample mean between 1.8 and 2.3? So that's going to be a normal distribution. I can write, not very well, with a lower limit of 1.8, an upper limit of 2.3, a mean of 2, and a standard deviation of a half divided by the square root of 50. And this is where it's nice that your calculator will do that calculation for you, because the square root of 5 divided by the square root of 50 is some ugly, long, irrational number. And you would need to carry that out probably to 5 or more decimal places to be accurate, but you can let your calculator do it and it's completely accurate. So we're going to go to our distributions, our normal distribution. Our lower limit is 1.8. Our upper limit is what? 2.3. The mean of this sample mean distribution of sample means and the population is 2. Again, the underlying population, the mean is the same as the mean of the distribution of sample means, the same mean, but the standard deviation is what? 0.5 divided by the square root of 50, close your parentheses. So normal, 1.8, 2.3, 2, 5 divided by the square root of 50, 0.5 divided by the square root of 50. Pretty much 100%, like 99765. To find percentiles, you're going to have to use the inverse normal. They'll give you what percentile they want the value for. And remember, percentile is how many were above spring break. Percentile is the number of values you're above. So if you're in the 95th percentile, that means 95% of the values are below whatever value you're at. So it's the area under the curve is what I'm trying to say. So a percentile is the area under the curve. To find percentiles for means of the on the calculator, follow these steps. You use inverse normal. You tell your calculator what the area is. That's actually the percentile that you're looking for. The mean. And since you're using central limit theorem, standard deviation is sigma over the square root of n. In a recent study reported October the 29th, 2012 on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15. We're taking samples of size of 100, find the 95th percentile or the sample mean age. So because we have the sample mean age, that means we're going to use the central limit theorem. So we're going to be using a standard deviation, which is the standard deviation of the population divided by the square root of n. So finding the 95th percentile, the mean is 34. The 95th percentile is this value right here. I don't know what I would call it, X bar. So I'm finding 95th. Let's do that. The X bar for the 95th percentile. So this area under the curve to the left of that percentile is 95%, 0.95. So we're going to use an inverse normal. The area under the curve is 0.95. The mean is 34. The standard deviation is 15 over the square root of 100. So if they give me the area under the curve and I need to find the average value that represents that area under the curve, I'm going to use inverse normal. So go to my distributions, inverse normal is number 3. The area is my percentile. My mean is 34. My standard deviation is 15 over the square root of 100. Yeah, I know, I probably would just be faster to type in 1.5. Trying to prove a point. So inverse normal, 0.95, 34, 15 over the square root of 100. 36.46. So 95% of the ages of tablet users is below 36 years old. Or 95% of tablet users' average age is, based on this central limit theorem, is 36. A retail company, and this is our last problem. So I'm going to let you out early. So what should you do? You should get this homework done. And you start your review for your exam. I think you have a quiz due today too, don't you? A retail company has a contract for their employees working in product manufacturing, and the distribution, which says that they receive a bonus pay. Let me reread that. A retail company has a contract for their employees working in product manufacturing and distribution, which says that they receive bonus pay if they can produce at least 102 products per day that are free of defects. On average, employees produce 100 products a day that are free of defects. The standard deviation is 10, samples of 50 random employees will be taken, and quality will be examined for a day. What's the probability the employees get a bonus? So why am I using the central limit theorem? There are two clues here that tell me to use the central limit theorem. On average, employees produce 100 products a day that are free of defects. So the average of this distribution is 100. And we're going to look at samples. So we're going to take samples of 50 employees and we're going to look at the average number of defects or free of defects they get. And we're going to look at the distribution of sample averages and we're going to look at the probability that the sample average is more than 102. So since we're taking a sample that is large enough, we are looking for the probability that the average number of items produced without defects a day is 102 or more. If it's 102 or more, we get a bonus. Okay, so our mean is 100. Our lower limit is 102. Our upper limit is as far right as we can go. The mean is 100. And the standard deviation we're going to use is the standard deviation using the central limit. So 10 over the square root of 50. So my lower limit is 102. My upper limit is 1 times 10 to the 99. My mean is 100. On average, we produce 100 items a day free of defects. And my standard deviation is 10 divided by the square root of 50. An 8% chance of getting a bonus. Wait, 07865. Are there any questions? All right. No questions. I'll see you on Wednesday.